Welcome everybody to our next video regarding the feedback control. Now we will talk about different types of controllers. So in the last videos we covered before what is a Laplace transformation and what are closed loop and open loop systems. And today we are asking the question, when we have a system like here, so a closed loop system or an open loop system, it doesn't matter too much. What is actually the value of ds? So what kind of a control transfer function are we dealing with? So the question is, the function ds, how does this function look like? And this really depends on the type of controller we are using. So at first we can use the most simplest controller, the so-called proportional controller, in short only marked with a P. This controller uses the input E and transforms it, as the name suggests, in a proportional way, so that the output value from the controller U is bigger or smaller in some proportional factor regarding E. So we can write down this transfer function in the time space as the controller output U from T will be a constant factor P, so a constant proportional factor, times the input, which in this case is E from T. So E from T times the proportional factor Kp will be our output ut over here. Now, because this is more easy to work with, we will transform it into the state space, which is actually quite easy. So the resulting equation will be a big U from S in this now, because we transformed it from time domain to state domain, and a big US equals the same Kp, so the proportional factor of the controller, times big E from S. Here now we can see that in this case the answer to our question, what is ds, so what is the transfer function from our controller here, is that the transfer function d from S equals Kp. So we have the constant transfer function Kp, which of course, because it's just a factor, remains constant. So this kind of control, the so-called P controller, so proportional controller, is actually quite often used because it has some advantages. It is quite fast, and especially in the beginning it is quite impactful, but then over the time it becomes less impactful because maybe our input signal, so if we have an input signal which rises and falls again, then it gets less and less impactful because it's just proportional acceleration or a proportional transformation of our input signal. So we can note that it is fast, but on the other hand it has also some disadvantages, because it can't keep our output signal at our desired value. So if we just have a proportional controller and we want to reach a value of, let's say, 10, then it is not possible with this controller, because just a proportional relationship between the input of the controller and the output of the controller is not sufficient to realize a stable output level. So we can note that it is fast, but it cannot keep us at the desired output value value. Let's call it u from t. Okay, this is the first type of controller. The second type of controller is the so-called integral controller. So I will note it here. The integral controller, also called I controller. This controller uses not a proportional, a constant relationship between input and output, but as the name suggests, integral relationship. So our output u from t of our controller will be some kind of constant factor kp divided by a so-called time constant ti times the integral from t0 till the current time point t from our input e, and then we close the integral with dt. So as you can see here, this integral controller takes the integral over our input value e and then multiplies it with a kind of constant. Here in this case we named the constant kp divided by ti. Now we can also transform this into the state space. So the resulting formula would be the big U from S equals, our factors here remain the same, so kp divided by ti times E from S. And because we have the integral over here, we just add for the integral here an S. So because the integral of, so the Laplace transformation of the integral is 1 divided by S. And so our resulting transformed function would look like this. Now we ask again the same question as before regarding the proportional controller. How does then our transfer function for our controller looks like? So the d from S. The d from S in this case equals this part of the equation. So kp divided by ti times the S. So what can we learn about integral controllers when we look at this equation? We can see that at the beginning the signal is quite small, because if you think about that, this when we integrate from 0, for example, to 0.00 something, so just a fraction of a second, then this part of the equation is quite small. So we know that it is not so impactful at the beginning, but over time, because we integrate over more and more time, the signal becomes even more impactful. So we can note down that it is small at the beginning, but impactful later on. So it gets more and more impactful. Okay, what else can we learn about the system? We can see that it will make our system less stable. So we can write down that it creates an less stable system. And we can also write down that in contrast to the proportional controller, it is able to keep us at our desired value, which is also a big difference. So it can keep us at the at the desired value. Yes, this brings me to the end for the integral controller, and now I will show you the third type of controller. Then the third type of controller is, as I said, the derivative control. So the derivative control is most often called just by the letter D, and this type of control, as the name suggests, creates the output signal U from T through the derivation, and it also adds some kind of constant factor before that. So we have Kp times Td for the time constant for the derivative control. And then we have the derivation of our input signal Et regarding the time. So when we would like to transform this, we create the following Laplace transformed equation. So we get a big U from S, which equals Kp times Td, and then we have just a simple S times big E from S. So what can we learn when we look at this equation? We at first can learn that in this case our D from S, so the transfer function of our controller D from S equals this part over here, so Kp times T D times S. And in general, you can see that this type of controller is very impactful when a sudden change happens, because then when we have a sudden change, this derivative part of the equation becomes quite big. So we can note down that it is impactful when we have sudden changes. So it is impactful when we have sudden changes in our system, and this of course has also a drawback, because on the one hand it is quite useful to have such a fast and very responsive controller, but on the other hand, if we have some kind of noise, or maybe some kind of background error or something, some kind of background noise, then this controller actually is quite problematic, because if you imagine a constant fluctuating signal, then this controller detects that there's a lot of change, therefore it also changes a lot itself. So therefore we get actually quite bad responses from this controller when we have a lot of noisy signals in our system. So we should mark this point here as well, so that we get bad signals when we get noisy input. So I wrote down here that we get bad signals, so bad controller output signals, when we have a lot of noise in our error signal, or in our signal we get from our feedback, because then this type of controller reacts very, very strongly to small changes in our noisy error signal or in our feedback signal. So we can also name this our feedback signal, and therefore we want to make sure that this controller is typically combined with other controllers so that we can balance this kind of disadvantage. And one thing which is actually quite nice about this controller, that like the exact opposite to our integral control, it makes the system more stable. So we get begin at So what do we learn about when we think about all these three control types together? We can see that each one of these has different advantages and also disadvantages. And therefore, in a real-world case, we typically combine these three controllers. So in a typical controller, we use a so-called PID controller. So what is this meaning? It means that we combine a derivative, an integral, and a proportional controller together to a so-called PID controller. And when we do that, we can basically combine the transfer functions. So we get all the disadvantages and advantages together, and therefore they can leverage you can leverage the total pool of the advantages and disadvantages so that they are balancing each out, against each other, so that in the end we get a more stable system which is nevertheless also quite fast and which is also responding to sudden changes, and overall the best of all of these three worlds. So how does such a system look like? So when we combine the transfer functions of these three controller types, we get something which looks like this. We have our output signal US, and this is created by a factor Kp times the components from these different control types. So 1 plus 1 divided by Ti times S plus Td, so which is the derivative control part, times S. And then of course this is like our PID PID transfer function times the input of our controller, the big E from S. So as you can see here, of course, this section is equivalent to our factor D, so our transfer function for our controller. So we can mark this one here as D from S, and then we can write this one in a shorter way, in a little bit compacter way. So we can say that D from S equals, so if we combine this Kp with the values inside this bracket, so then we get an Kp plus the K integral divided by S, because if you imagine we multiply it in there, then we get Kp divided by Ti times S. So we can combine Kp divided by Ti to this value Ki, and then we have just the S here in the lower part, which remains, and then we can do the same thing for Kp times Td, and we can call this the new Kd times ds. So here you have the transfer function for our PID controller, and yes, with this you can work quite easily to control these kinds of systems, and furthermore you can use this transfer function to analyze different kinds of system behaviors or other characteristics you might be interested in. Thank you very much. This covers it for our video regarding the different control types, and see you in the next one.